Okay, I think you should be able to see my screen, right?
Yes.
Yeah, perfect. So today we are going to introduce you all the new functionalities of the 2021b version for PSIM and DSIM, and the new functionalities as well for the SmartCtrl 5 version, okay, which will be released soon. So for PSIM and DSIM, those new versions have already been released, so you can download it from our website. But for SmartCtrl, it will be ready very soon. So I will just introduce Powersys very quickly because this is not the main goal of the webinar today. Then I will present you quickly PSIM with the main function and now the new features of the last version. And I will present you as well the DSIM new version. So Vishwa will do this and SmartCtrl as well. So let's start with Powersys. So Powersys, we are a company with a lot of expertise, and we are a provider of simulation software. We provide some expertise in consulting as well, and we can help you to design all your need regarding the electromagnetic parts, the power electronics, multiphysics system level, CFD for computational fluid dynamic, and power system. So we have been created in 2002, and we have 8 offices around the world. As you can see, the headquarters is in France, in Aix-en-Provence, and we have a lot of offices in Germany, in India, in Canada, and USA. And we are around 50 people. So we provide a lot of different simulation software depending on your needs, and we provide also some services like technical support, like webinars, like also video. We provide also some training, get started training for PSIM, or some application training linked to PSIM as well. And we provide also some consulting services. If you have a real interest, feel free to contact us, and we can also help you and help to design what you want to implement. So you can see directly here all the simulation software that we distribute. Okay, so we distribute different software depending on your activities. It could be in electromagnetics, it could be in power electronics, multiphysics, CFD, and power system. And today we will be focused on PSIM, SmartCtrl, and DSIM. Here you can see our business area because we work not only in consumer electronics, but we can also work with our automotive manufacturer, aerospace and defense companies, transport, electrical energy, renewable energy, electrical vehicle, and so on. And here you can see some famous customers that we used to work with, depending on the software. And here you can see our contact. If you want to contact us, you can directly reach us through this email address. So let's go to the PSIM part. So PSIM is developed by the company PowerSim in United States. Okay, so this software is born in 1994. Okay, for people who want to design any power electronics circuits and motor drive. So Powersys, our company, we are the exclusive distributor in Europe, and PWSIM is the distributor of PSIM for India. And so PSIM is used in more than 70 countries worldwide by thousands of customers like Samsung, John Deere, LG, NASA, and so on. So as I have mentioned, PSIM is a simulation software specifically designed for power electronics, motor drive, and energy conversion applications. So PSIM is between space simulation and MATLAB Simulink. So you can use SPICE for device simulation. So you can use LT-SPICE component into PSIM and use the SPICE engine in order to simulate your circuit. And you can also use MATLAB Simulink if you want to make a kind of co-simulation. So part of the circuit could be done in PSIM and the other part could be done in Simulink. And you can then exchange data between those software in a co-simulation. Okay, so Simulink is mainly used for system and control simulation, and PSIM is more focused on power stage. This is why you can use both in this kind of way. So PSIM also could be used itself if you want to design all your power and control strategy. Okay, so this is a complete tool for power converter simulation as well. Okay, from device to system level. So you can improve the accuracy of your system depending on the components that you want to use and the degree of level that you need. Okay, and PSIM is widely used for simulation speed and result accuracy because it doesn't suffer of convergence, and it is very robust software because since more than 20 years, PSIM is improved every year, and we collect all the feedback of our customers and we try to improve with new functionalities depending on the feedback we have. So one of the main features of PSIM is quite friendly and easy to use. So I guess most of you are the main users in your company, and I think you like PSIM because it is quite easy. Okay, you can drag and drop some components, you can build your system and check the result thanks to the SIM view, the post-processing part. We have also fast and robust computation engine, and we have integrated also the DSIM engine, which is the fastest engine of the world. Okay, we have a lot of components depending if you want to work in analog domain, okay, in digital domain. So you can directly move from S to Z domain in a couple of seconds by using some digital control tool. You can also generate code automatically. You can write your own code manually. You can use our C block for control stage strategy. You can use also our thermal module if you want to scan the curve from data sheets of your MOSFET IGBTs, for example. And at the end, you can directly calculate the losses of those IGBTs, MOSFET, inductors, and diodes, depending on the curve from the datasheet. So the losses will be quite accurate because if you use the datasheet in a correct way, in a proper way, okay, the losses will be calculated according to this curve. So you can also use PSIM with MATLAB Simulink, with GMAG for finite element analysis simulation, for electromechanical simulation. And we have also the new link, the new FMI, the functional mockup interface between PSIM and any other software compatible with FMI. So we will go through this FMI link during this presentation. And also, we have the design suite capabilities, which can help you to design in a few minutes and in an automatic way any LLC power converters, any EMI simulation as well for electromagnetic interference, and also the motor control design suite if you want to drive to pilot a motor, and finally if you want to work in hybrid and plug-in hybrid electric vehicle, you can directly use those design suites, which are kind of templates in order to help you to design the power stage and to design also the control stage and to make something very clear without any trouble and with a good accuracy. So here you can see all the environment around PSIM, all the modules that we that you can use directly in order to have a complete environment from design simulation software with SmartCtrl, for example, and the design suites for LLC, EMI, motor control, and hybrid electric vehicle through PSIM with the power electronics capabilities, renewable energy, optimization, device simulation, loss calculation, digital control, code generation through then directly to the implementation with hardware, because PSIM could be compatible, is compatible with a lot of microcontroller from Texas Instruments. As you can see, the different families here. And for FPGA as well, you can use the PE Expert 4 and Model Sim if you want to make some FPGA simulation. And you have the capability to use the IL link between PSIM and Typhoon IL as well for hardware in the loop. So let's go to the main features of this new version, the 2021b. So the main new features are shown directly here. Okay, so basically we have integrated new tools, new analysis into PSIM. We have the Monte Carlo analysis, sensitivity analysis, and fault analysis as well. So we will go through each kind of simulation in a few seconds. We have the FMI new link, which help PSIM to co-simulate with any other software compatible with the FMI link, the functional mockup interface. We have also improved the new EMI, the EMI design suites in order to add the capability to use three-phase system. So previously it was only for one-phase system, okay, but now you can use three-phase LISN, three-phase filter, for example, okay. A new type of filter have been added as well. Also, regarding the LLC design suite, okay, the power supply design suite, we have added a new topology, which is a CLLC topologies. Okay, so the principle is the same as you use for the LLC, just the topology has been changed and has been added into the new tool. So thanks to this new topology, you can directly build again your power stage, your control stage, and simulate your resonant topology like this. We have also added the capability to use PSIM and GMAG-RT for the 6-phase PMSM and synchronous reluctance machine. Okay, so PSIM and GMAG-RT are already compatible. Okay, but now if you want to use 6-phase PMSM model from GMAG-RT, you can use. So as you know, GMAG is a finite element analysis software. It's a 3D simulation software, and GMAG-RT is 1D. It's a kind of lookup table, okay, of your motor parameters. So you can export your GMAG motors from 3D to 1 dimension, okay, 3 dimension to 1 dimension, and this motor could be then exported into PSIM. So this capability was already present, but now you can use directly the 6-phase PMSM RT model in order to have something very relevant. So again, it depends if you want to work in motor drive application. Also, we have added the capability to support the sigma delta frequency modulator. This is a new component, it's a new filter, in fact, inside the code generation capabilities for microcontroller topologies. We have added the capability to check the netlist when you want to import a PSPICE model into PSIM. You need to check if the netlist is compatible with LTSPICE, because only LTSPICE is compatible with PSIM. So now you can directly check and compare the PSPICE model netlist against the LTSPICE netlist and check if the netlist is well transcripted. You can then use LTSPICE directly. It will work. So it will give you the compatibility or not between the PSPICE and LTSPICE engine, depending on your netlist. And finally, we have added 5 new application nodes. It is basically based on different applications that you can use in PSIM for code generation, AC sweep, so frequency analysis simulation, how to do that, how to use PSIM and SmartCtrl for closing the loop of buck converters, of LLC converters. So you will have a lot of new application. It's a kind of tutorial which can help you to go further with PSIM. So it's not only a tutorial based on tools, it's a real tutorial based on applications and how to do that in PSIM, depending on what you want to set up for motor drive, for LLC, for a lot of applications. Again, you can find those application notes directly into the PSIM installation folder inside the application folder as well. Okay, so now let's start with the main new feature. So I will talk about the Monte Carlo, the sensitivity, fault analysis, and FMI. I will just show you directly how it works. Okay, so the Monte Carlo analysis. So basically, the Monte Carlo analysis, okay, allow you to estimate a numerical quantity using random numbers. So Monte Carlo analysis determines how design performance change as component parameters vary from their nominal values. So the parameters value are given a range of value according to distribution function, and multiple simulations are executed. Okay, so it will done randomly. Okay, so basically it will study how parameters variation affect the output with different law. So we have integrated a lot of law: uniform, normal, so this is a Gaussian, as you know, triangular, and so on. Okay, so we have added those those statistical distribution law. Okay, and depending on this law, directly PSIM will use the minimum and maximum range that you have set up, and PSIM will execute randomly a lot of runs, maybe 1,000 runs, in order to check the distribution of your simulation depending on your parameters. And at the end, you can directly check the result through histogram, for example, because the simulation result will be directly collected and could be presented, like as you can see here, with histogram and scatter plot and Pareto charts as well. Okay, so the Pareto charts will identify which parameters have the most effect on your performance deviation. So you can see the mean, okay, of the simulation, okay, of your system, of your output, and you can check the standard deviation between the mean. Okay, so you can have this kind of histogram which will be plotted automatically depending on your Monte Carlo analysis. So I will show you now a quick simulation. Okay, so here you can see this three-phase rectifier, which is in open loop. Okay, it is quite easy to understand. So in fact, when you want to use a Monte Carlo analysis, basically, you need to avoid to directly give a value. So now you have to skip the value of your capacitance and for the resistance as well, because we want to make a variation of your capacitance and variation and resistance. So basically, now if you simulate, it will not work. Okay, the transient simulation will not work because it is undefined. Okay, I give a value to the capacitance and resistance, and this is normal. Okay, so remember that you have to give a name to the value. Then you have to go into the analysis and click on Monte Carlo. When you click on the Monte Carlo, as you can see here, you have a window. And now this is the Monte Carlo analysis window. So for example, you have, as you can see, the tool is directly recognize the different parameters with the name, capacitance and resistance. This is the name of my value. Then I can choose a different uniform and different distribution law. So I will select uniform and I will put the minimum value, and maximum value here, like this. Then you have to do the same thing for the resistance. So it will vary between 4 ohm and 10 ohm. So it means my simulation will change randomly my capacitance and my resistance according to this value. This will be the minimum and maximum value to not exceed. Then into the output measurement, you have to decide here the name of your output, okay? and this is just a name, and you have to define which signal you want to check. So as you can see here, I have my VDC voltage, probe. So you can define your VDC and what you want to check. So for example, I want to check my steady state. So I want to measure the steady state of my output voltage depending on this variation. Okay, it's not a parameter sweep that you used to know. Okay, because parameter sweep will go from one value to another value with a step. So here there is no step, it is randomly. And here basically you can define the number of simulations, the number of runs that you want to use to simulate. And now you can save your result if you want to check the report, if you want to check the different simulation files, the different simulation files, sorry. So you will have 500 simulation file, and now you can click on run analysis. Okay. Sorry, Monte Carlo. I don't know. Sorry for this small issue. My computer maybe is having some trouble. So I will just add resistance. I will do it quickly. Just redo the step. BTC, steady state, add, yes. Yeah, now it works. So as you can see, the simulation is running now with the 500 runs. You can see the simulation time directly here. And now it's done. Okay, so basically now you can see the output voltage depending on the different simulations, the 500 simulations. Now you can directly check here and rank the output voltage against the capacitance. Okay, as you can see, and here against the resistance. And now, and I think it was already clear for you, you can see directly that the output voltage is directly depending on the value of your resistance. So if the resistance has the biggest value, as you can see from 4 to 10 ohm, the output voltage will change and will increase. So directly here, you can see the correlation between the output, I mean the steady state output, okay, against the different parameters that you have selected, capacitance and resistance. Of course, you can modify also the MOSFETs, the IGBTs, you can modify this value, you can modify the control stage, you can use any component, okay, and the tool will detect automatically the component, the parameters with a name directly. And you can also plot with the histogram, as I have mentioned. Okay, so you have the standard deviation, you have the mean. Okay, so this is the average value, in fact, of your output voltage depending on the different runs, the count. Okay, standard deviation as well, and you can see the CDF, which will give you just a distribution. So as you can see here, as the mean is 160, you can see that 50% of the proportion is below the 160 and 50 other percent is above this value. So it's just a proportion against the output voltage. Okay, so you can check the statistical law like this, and you can check the correlation. So this is the Monte Carlo analysis. Okay, so now let's go to the sensitivity. So the sensitivity analysis is a very useful and helpful, okay, analysis, because this analysis will be used to determine how sensitive a specified design performance measurement is to variation in design parameters. It means depending on the parameters that you want to study, okay, depending also on the measurement that you want to implement, the tool will give you directly the most sensitive parameters. And these most sensitivity parameters will be the parameters that you need to take care, that you need to be careful, because if, for example, the resistance or the capacitance is the most sensitive, it means you will need maybe to make some double effort, because if the value of the resistance change during the years, the output voltage will not be the same. And then you will have maybe some trouble, some damage into your system. So the sensitivity analysis is the first analysis to do when you want to make some measurement and you want to know which parameters affect the most your circuits. Okay, so basically the sensitivity analysis is again very quick and simple to realize. So you have to click on analysis. We will take the same circuit, the three-phase rectifier. You can click on sensitivity. The new window will open. And here you can directly give the nominal value of your capacitance. At the origin, as you can see here, it was 200 micro. So I will use my 200 micro and I will give a variation of 5%. Then I will again use the resistance, and the original value was 5, sorry, and I will add a 5% variation. Now I will directly check again the steady state, because this is what I have done for the Monte Carlo analysis. So I select my output voltage, which is a VDC. I select the steady state here, and I click on add. I can again save the result, because you will have a report and some results directly, and you can run the analysis. And as you can see, the analysis is quite very short and quick to set up, okay, because we use this kind of equation, okay, and depending on the variation and on the nominal value, okay, you can see that directly which is the most sensitive component, basically here. Okay, so you have the ranking value here, and you can see the most sensitive value. So in this case, we are here the capacitance. Okay, so if you check your circuit, the capacitance will be the most affected your circuit. So in a very few steps, you can directly check the ranking, and depending on the number of plus, you will have directly the ranking value like this. Okay, this is for the sensitivity analysis. And now I want to talk about the fault analysis. So basically, the fault analysis is a very interesting tool, because it will allow you to apply some fault inside your PSIM schematic and monitor the result. So the goal is directly to understand the impact of any fault on your system behavior and check if the system is still on your operating safe area. Okay, so we can have several causes, okay, as a fault. You can have the component aging, okay, because it will vary during the lifetime of your component. You have also the EMI influence, and also you have the temperature of the system, which can have a real impact. And you can directly add any fault into your system automatically. It could be a short circuit, it could be a parametric fault, so you can change directly the value of your parameters during a simulation, and it could be also an open circuit. Okay, and we can directly at the end make some test case, okay, because you have the test case capability here, and check if the safety criteria from user specification are violated or not. Okay, so we will do that right now. So I still open my my three-phase rectifier, and only for this case you have to skip what I have told you before. You don't have to give a name, you have to define a value. Okay, so now you have to do as you used to do, give a parameters value during the simulation. And if you run it, as you can see, I can check the VDC because the transient is working well. So now you have to click on the fault analysis. So all the new tools have been added directly here. Okay, so you have the new tools, the new fault analysis directly here. So now let's say I want to shortcut my RL1 component. So you have to click, you have to give the name of your faults. You have to select which kind of fault you want to use. So on the parameter fault, you can make an open circuit. For example, if you want to add a large resistance, but I want to shortcut the RL1 directly here. And now which pin I want to shortcut. So when you click on the component and go on sorry, generate netlist, okay, XML, it will directly open the netlist of your RL1 component, of your rectifier. And here, depending on the RL1 of your component, you can see directly the position of X and Y of each node. Okay, so this is a geographical position of your signal. Sorry, I will just put it small here. So you have this, you have the position X and Y to this node, X and Y to this node, and so on. So like this, you can directly understand which pin you are going to shortcut. So for this simulation, I want directly to shortcut the pin 0 and 3. 0 and 3, which is in fact like this. Okay, so if you check the netlist of your component, you will understand quickly that the pin 0 and 3 are those pins. Okay, so I will just like this, and now you can click on add. Now you can make a test case, okay, because you want to check if now your VDC is, for example, greater, so your steady state is greater than 50. So if I shortcut this component, I want to know if my voltage is above 50, because maybe 50 is my critical maximum value to not overcome. Okay, I can click on add, and now I can click on yes, and run the analysis. And as you can see now, the value of your output voltage now, if you shortcut this 0 and 3 pin node. Okay, so yes, the test case is valid because it is greater than 50. It is around 250. Okay, so like this, you can add any test case in your system, make any fault into your system like this, and check if it is violated or not your safety criteria. Okay, perfect. So here we have also the new function for the EMI and filter design. So we have added new P-type and T-type filters. Okay, in addition to the L-type filters, we have included the new ESR and ESL, so you know, equivalent series resistance and inductance to capacitor CX and CY, and the interwinding capacitance to common mode shock. These are the new parameters that have been added into the filters in order to have something very accurate. We have also added the damping branch to filters with new parameters as well. A new ground plane if you want to have different ground in your system at the primary and the secondary side, for example. And we have also added the capability to support the three-phase system with the filter, with the LISN and signal analyzer for checking the common mode noise, differential mode noise, and so on. And finally, we have also added a new template regarding the three-phase Vienna rectifier. Okay, so this is new. So this is into the design suite. You have to go in EMI directly. You can check the Vienna rectifier here. You have to unpack it like this. And here you can see the three-phase system LISN, three-phase filters, different ground plane, and all the parameters inside the filters, as you can see here. Okay, with the damping, as I told you, the ESR, ESL, basically here, and you can directly check how the L type and P type have been built and added, and you can directly choose on those three different filters. It depends on what you want to use, and also the common mockup, which is really important, has been added like this with the different equations that you can have. So everything is quite well explained into the tool. Okay, so you can basically have a quick overview of this three-phase of this VNR rectifier and the other template, and you can directly guess and make any simulation depending on your needs. If you want to, if EMI is something relevant and interesting for you. Okay, you have all the parasitic common mode capacitance, as you can see here, and so on. You have your control stage, basically, which is done like this with a PI block in order to close the loop. So you have something very relevant and stable. Okay, and you have all the main parameters to modify depending on your needs as well. So here you can see the different filters I have mentioned, the new block which have been added for the three-phase system. So for the power supply design suite, which is another design suite for LLC converters, this new template CLLC have been added. As you can see, the CLLC, okay, for the primary and secondary, okay, have been added. And if you know this power supply design suite, I think you will not be so lost, because this is the same way, but just the new topologies, as you can see, have been added with the same control loop as you used before. Of course, you can still use another software like SmartCtrl if you want to close the loop, okay, because here it's a feed-forward control, but you can use the inner control loop, the outer control loop, and use the different PI given by SmartCtrl, for example, okay, and you can directly modify the input, the output voltage directly, and the power, and check the different parameters like the quality factor, the inductance ratio, okay, against LM and LS, okay, the magnetisant and this LS value, and directly the sampling, the frequency directly between the resonant frequency and the switching frequency as well. So you can play with those parameters, check directly the steady state, I mean the solver, which will give you the main curve to check, and directly sweep the quality factor, sweep the inductance ratio directly, and observe the difference on the gain, on the frequency, and so on, and make the best trade-off depending on your converters. So this kind of converter could be used in onboard charger vehicle if you want to work in this, if you are working in this kind of domain. So a new 6-phase PMSM model have been added, but now with zero phase shift. Before it was 30-degree phase shift, but now it is with 0 phase shift. Okay, so feel free to use this model if it was also one of your needs. We have added the 6-phase PMSM with GMAG RT, as I told you, and the synchronous reluctance machine model with GMAG RT. So you can use the accuracy of GMAG and export into a kind of lookup table, which is a RT table, okay? And at the end, you can use only PSIM with the RT model from GMAG if you are working in motor drive application. So the thermal module have been improved as well. Okay, for example, when you select one of the IGBTs that you want to use, you have directly the list here, as you know, and when you click on go to devices, it will open automatically the thermal tool, okay, in order to check the different parameters, the different curves which have been added into the main tool. So it's just something new, but it's mainly for a graphical interface, okay, which has been improved. So you can click on go to devices and the tool will be open directly. You don't need to look for the component. Okay, and check the properties. You can change them, you can modify the curve scan, and at the end you can check the losses, the junction temperature as well of your power converters, of your inverter here in this case. And also the those component for those two families have been added. This is the SDFM, this is a sigma delta frequency modulator. Okay, so basically this is just a digital filter, okay, designed specifically for current measurement and resolver position decoding in motor control application. So if you want to use this model for code generation, it will be possible for resolver position and current measurement in motor control applications. So you can generate code automatically now with this new component. Okay. And as I told you, we have the tool to check the PSIM netlist here against the LTSpice netlist that you will use inside PSIM. So basically, you will have some suggestion in yellow color, as you can see here. When it is possible, you will have the suggestion, and then the model will be changed then in order to use it. Because if you use a PSpice model which is not compatible with LTSpice, you will have some trouble during the simulation. So you have just a tool which help you to know if the netlist that you want to use is compatible with LTSpice. And last module before to go to DSIM new features, which is the FMI. So as you can see here, okay, the FMI, okay, is a standard norm that you can find into Google. So if you type FMI, so functional mockup interface, you will have a website, okay, into an official website. Okay, and in fact you will have the description about what is the FMI capability. So in fact the functional mockup interface is basically an open standard for exchanging dynamical simulation models between different tools in a standardized format. It's a combination of XML, binaries, C code zipped into a single file. So PSIM has the capability now to generate an FMU, a functional mockup unit, okay? And this FMU could be loaded in any other software which support this FMI capabilities. So for example, you can link PSIM now with a computational fluid dynamics simulation software, for example, or with a mechanical software. But this software needs to be compatible with FMI. So if both software are compatible with FMI, you will have the capability for now to send FMU circuits, okay, from PSIM, and you will be able to load this circuit into this external software. Okay, so actually PSIM will be treated as a slave. Okay, and it will be a co-simulation. It's not a model exchange. Okay, we will make some improvement in the future, but actually it's a co-simulation, and PSIM is a slave. So it means you need to export the FMU from PSIM into the software. You cannot import FMU into PSIM. Okay, it's just exportation from PSIM into another software. So I will show you quickly how it works basically. So I will open my example with FMI. So just 1 second. Like this. Okay. Perfect. So I just want to show you the demonstration with MATLAB Simulink. Okay, because I have MATLAB Simulink into my computer. So basically here, what I want to do is I want to send the output voltage and the current through the inductors to Simulink, and Simulink will give back to me the modulant, the modulator value, the VM value, in order to compare here and get the PWM for these buck converters. Okay, so we have to define directly the ports input and output that you want to exchange. Okay, so the power stage is in PSIM and the control stage is in Simulink, but basically you can define any signals between both software. Okay, so here I have decided now to give a name again. So if I simulate this circuit, it will not work because res is not defined. Okay, so basically if you go on option on utilities, export FMU, you will have the interface of the FMU, which will be automatically open. And again, depending on the input and output node, because here, as you can see, it is an input in link node, and here you have the out link node. Okay, so depending on this, on the number of input and number of output, the tool will detect automatically. So I have input 1 VM and 2 output with current and output voltage. And here, as you can see, this parameter res has been automatically detected in order to exchange it during the simulation. Because if you want to modify parameters or more parameters during the simulation, you can do that by directly select the component here. And here, at the end, you have the capability during the simulation at the end, okay, to open SimView if you want to check the result into PSIM or if you want to check it with Simulink. And here you have the time step of PSIM, okay, which will be used during the co-simulation between PSIM and Simulink. So now the thing is you have to click on generate FMU. So when you click on generate FMU, basically here it will directly generate automatically this FMU. Okay, it will be generated automatically. So now you have to open Simulink. Here you have also to open the circuit. So this is this circuit. So I can click on open. So I have it directly. So it will take some seconds to open. Perfect now. And here you have to go into the library. Okay, sorry. Here you have the library with the FMI. Sorry, FMU. This is FMU. Yes. Now I have my FMU block. So I can delete and I can directly specify now my FMU. So I need to go into my PSIM. Okay, so if you remember, this is my PSIM folder where is located my example. So I can directly go here. And as you can see, this is my FMU that I have generated. When I have clicked on generate FMU here, it will generate it directly here. So now let's go to Simulink and click on FMU. So I need to add the path. Okay, apply and okay. So now I can just reduce like this. And as you can see here, I have my FMU with my two output and my input. And now, okay, you have your control strategy in Simulink, your power stage into PSIM. And now you can run the simulation. And at the end, as you can see, you can check, for example, my output voltage, which is 12 volt. So the co-simulation has run in a few seconds, okay, milliseconds, okay. And now this is the result from PSIM of your output voltage. And also you can check the output voltage from Simulink if you check as well. And you can see directly here, if you make a quite small zoom here, like this, the output voltage here. So like this and like this. Okay. So directly you can see it is 12 volt as well. So basically Now with PSIM, you can use PSIM and any other software, not only not only Simulink. Simulink is just for an example today, but if you have any other software compatible with FMI, you can directly have access. So if you want to check, you have to type functional Mockup Interface, and when you click here, this is okay. Sorry, I have functional Mockup Interface here. This is the website with the FMI. So PSIM we encapsulate is FMU into some files, as you can see here, and this file could be loaded in any other tools. And here you have the list of the tools compatible with FMI capabilities. So on this first case, PSIM will be used with a co-simulation, okay, with any other software. And to finish with PSIM, you can here now, so new example have been, new element have been added, okay, some, for example, the bus bar, the coaxial cable, the new control element, space vector PWM in 3 level, for example. So we have added new component directly, and the different application nodes, as I have mentioned, which can help you to directly use LLC converters, how to make some AC analysis, okay, for bug control, for bug converters. So it will give you new tips and a very good process in order to do what you need. You can also check the power loss and efficiency calculation of any resonant converters, but it can be applied to any power converters in general, and how to use as a LLC design suite for wireless power transfer application, and how to use Monte Carlo sensitivity and fault for LLC converters as well. So these are news. And it could be very useful if you install this version, it will be directly available for you. So now I will let Vishwa talk about DSIM. So I hope you have again some minutes for us. So thanks, and Vishwa, thank you for doing DSIM.
Thank you. Yeah, thank you, Adrian. I'm just sharing my screen. Share. Okay, I hope everyone can see my screen. So yeah, so as of now you have seen the PSIM new features, and let's dive into the DSIM part. So if someone don't know about the DSIM, so DSIM is a new simulator solver that can be either purchased along with the PSIM, or it's an add-on mod separately you can able to procure. So it's a capable of simulating simple topologies or large and complex systems with outstanding speed and accuracy. So for example, if someone want to work on 1,000+ switches, so the simulation of 1,000+ switches, so in order to evaluate or in order to simulate, for example, like 100 or into 1,000, so the simulation time will take some time. So but in DSIM, as is a faster solver, it can be simulate within minutes and within seconds to within minutes. So it has a fast switching frequency. Even it can able to work with megahertz also, from kilohertz to megahertz. And it has a non-ideal switch transitions like physical models with parasitic effects. So you can able to enter that. And even it has a switching tangent simulations. So you can able to provide the switching tangents. So in the solver itself, we can able to provide the switching tangents option. And even we have a scripted tool, and automatic simulations can be possible. And it has a super fast AC sweep analysis, which I'm going to show you today. And these are the key features, new features available in the DSIM in the version 2021b. So coming to DSIM, it's very novel technique of solving power electronic simulation, was specially designed to address schematic with a larger number of switches, high switching speeds, the need of small time constant, because everyone want to complete the simulation with a shorter time. So everything can be completed in the shortest time with a constant for switching transients, and even large time constant, including the nanosecond timing with switching transients. All these things can be possible. So coming to the latest version of DSIM, which has been released with some impressive new features. So there are some critical new features for users who focus on control, or for users more interested in power hardware or switching transients. So coming to that, so let's segregate in that. So for the control side, you are now able to use the time domain AC sweep analysis, which you can able to see. And so we can do the SUC on something like voltage balancing or current sharing on and multi-mode converter stage and get results in a quicker time. So from even from the 5 hertz starting frequency and 2 megahertz frequency, you can able to do it. So apart from that, it also can do SUC on droop control of multiple converters working in parallel. So that is one good feature we have. And combining with this frequency response, so along with the smart control, which I'm going to show you, so the closed loop formation of very complex systems can be designed. So these sort of multiple time domain simulations would take huge amount of time with existing tools, but on the other side of the power hardware side, the switching transients can now come out of the switch module and interact with the rest of the circuits. So that's why we added the switching transients in the entire circuits. Previously, the switching transients was based on inside of the switch module. So we have I'm just showing in the coming slides how this particular thing will be available. So we can able to see the only ideal waveforms, but in this latest version, we added the switching transients. So this will enable you study the conducted EMI part for larger converters quickly and effectively. So these are the new features which I'm explaining in detail. So like switching transients, new SUC functions, we have the DLL blocks also, which is currently supporting. And one added advantage will be the automatic conversion comparator-based PWM. So earlier, DSIM can able to support only the digital part. Now, even if you are entering doing your control part in the analog, so it will convert to the discrete domain and it will do the analysis. That's what we have provided, automatic discretization of S-domain blocks, and many new elements and examples we added. So without any further delay, I'll just show you the couple of things. So one is the main feature is the switching transient simulation. So as you see, this is the one rectifier which we have. So where in the solver settings, we added this enable switching transients in the downside, you can see that. So if it is 1, so that means it is enabled. So where we are including the switching transients, and we can able to see the performance of entire transients in your screen. So this is what we offer in the new simulation, new feature. So with this, you can able to perform the EMI simulation also by running this particular thing. So this is one thing, and we have the AC sweep analysis. So we can able to do the AC analysis. So if you remember how we are doing in PSIM, so the same way here we have AC sweep block and AC sweep probe. So only the added advantage here, we are using direct blocks, like nothing but we are using buck converter or boost converter or inverters, anything, as we are using a switch models directly. So no need to place any switches. Direct we have a switch modules available in DSIM. So coming to the AC sweep analysis, generally it is a time consuming because of the frequency, how much frequency you are running. So initial conditions, if you are working with a low frequency, the time will consume a lot, but once the frequency is going, the simulation also will be increasing. But in DSIM, so from the starting itself, the simulation speed will be very fast, and you can able to see the results very quickly. So these two things I'll show you quickly on this tool. So then we'll see. So hope you can able to see the particular screen. So we have the option. So if someone don't know how we can able to do the settings, so here in the PSIM only we can able to do the settings. So I'm using along with the PSIM, right? DSIM. So in the PSIM we have a advanced options. So in that options you can able to select the elements compatible only with your either with PSIM, DSIM or SPICE. So for example, I'm just selecting the elements only with DSIM. So we'll see number of elements right now we have available. So if you see here, we have power. In the power, we have RLC branches. So like this, all the components are available. In the switches, we have different switches and switch modules. So we have buck boost and 3-phase inverter, T-type, NPC type, dual active bridge, everything we have. So even we added everything, and even the transformers are supporting. And in the motor drive, we have squirrel cage induction machine, PSIM motor, and synchronous machine currently. And in the renewable side, so solar module, because the DSIM will be more useful for the microgrid application who are working, because in microgrid applications, the number of switches will be more and the simulation time will be more. So in order to perform the very faster simulation, so for DSIM will be very helpful. So who are into that particular research part, so DSIM will be very helpful for that. And even we added so many control parts, so including the PLL blocks and zero order hold, all the digital blocks we have provided. And we have the sources. So we have voltage and current sources as like in PSIM. So for example, let's see this 3-phase PWM inverter. So where I'm having a three-phase inverter with SSC MOSFET. So here you can able to change the model level directly. So either if you want ideal model or average model or IGBT model or SSC MOSFET, you can able to select. So if you're selecting SSC MOSFET, so it will it can able to select the device over here. So if, for example, if I'm just selecting this particular device, so I can able to go to device also directly. So this is what we this is option which we have mentioned in the PSIM also. The same is available. So here you can see the database editor. In the same, we added one is for PSIM and one is for DSIM. So here you can able to add your graphs directly from the data sheet, like IDS versus VGS and CSS or CRSS versus VDS. So directly you can able to add how you are adding in the thermal database editor. The same you can able to add it for DSIM itself. So the component, I mean the element will be available for both PSIM as well as DSIM. So this is one option we have provided in the latest version. So directly the user can able to go to device without checking in the device database editor. And coming to the simulation settings for the DSIM. So we have provided in the DSIM part, you can see we have two types of solver type. One is D side and one is BD side. So in that we added the other functionalities like enable switching transients out. So we can able to either enable or disable it. So right now I'm just enabling with my SIC MOSFET. I'm just running the simulation. So I'm just running the simulation with run DSIM. So I'm not running a PSIM simulation over here. I'm just running DSIM simulation. So you can able to see the speed of the simulation for this entire schematic, how much time it is taking. So it will run very quickly with the frequency and you can able to check the results. So it took around 14 seconds to complete it, and directly we'll get the results over here. Let me load the design. So here you can able to see the results. So for example, I'm just taking the particular switching transients. So directly can able to check this switching transients over here. So this switching transients you can able to check over here in this particular waveform. So like this, you can able to check the switching transients directly along with your which you have included. So which will be very useful for getting the switching transients. So that is one thing which you can able to check it in the DSIM part, and the other part will be the this AC sweep analysis. So in the same AC sweep, so here I have a buck converter, so where I can able to provide the switching resistance of my buck. Which is a direct model which is available, no need to create anything. So directly you can able to take it from the switch models and you can able to complete it. And the added advantage here, we added the ACC block. So how we are using in the PSIM, the same we can able to provide. So what is the start frequency and what is the end frequency and the total time, number of points, and the perturbation which you are injecting into the voltage. So this particular source name and the injection voltage should be the same. So the same thing we are providing over here also. And directly you can run the DSIM simulation. So you can be able to check the results directly. So in order to, I mean, the entire results will be very fast. Even for the smaller frequency, you'll get the entire simulation can be simulated in a shorter time. So like that, you can able to increase the frequency part and you can able to check it. And even we have a number of examples for DSIM. So you can able to check that in the DSIM part also. We have created a number of cases like in PSIM. So even for I mean, for example, let's take one quick example on the three-phase inverter, which I'm taking 9-level cascaded multi-mode. So I'll show you the difference, how it will be helpful. So here I have around 48 switches. So each leg has 4 switches. So here I have 16, and here in this leg I have 16, and here I have 16. So 16. So total I have 48 switches. So so let's see how DSIM and PSIM simulations. I'm just comparing along with the PSIM itself for your time, I mean, for your reference. So here I'm running for total time for 0.1 seconds in PSIM. So initially I'm running the simulation with run PSIM simulation. So this will take around 20 to 25 seconds in between. So and we'll check the same in DSIM, how the accurate results we can able to get it in a shorter time. So even if you want to see some analysis over here, so all this we are having the PWM direct blocks are available, which is in Z domain. So as I mentioned, even you can able to utilize the analog domain and it will discretize directly into Z domain. So it took around 31 seconds because of the internet which I'm using. I mean, because of the processor. I'm just taking the VAB output. So here I'm getting around 700 volt. So 650 to 700 volt I'm getting. So I can able to check the same result. I mean, check the same simulation with the same schematic by using what I will do with the same. I'll check with the DSIM part. So in the DSIM, I'm just running for n time as 0.1. So which I'm using a DSET, which is a non-stiff solver, which I'm using. And here I'm running the simulation. So we can able to check the simulation time over here. So this is for PSIM, and let's take for DSIM part. So it took 1 second to complete the simulation. So if you are increasing more switches, the simulation speed will be more. So that is the advantage in the DSIM. So where you can able to where you can able to utilize for faster simulations. So coming to the other things, like what are the other supported blocks we are having? So we are currently supporting the DLL blocks. So directly we can able to write the code and we can able to add the code into your DLL and you can able to run the code. So even the custom C code can be compiled into a DLL part. So once you are done, you can able to load it in PSIM, in the DSIM directly. And this is a major version, comparator, we are supporting right now. So comparator based PWM, it can be converted directly into the digital part to compare it. So that is automatic conversion of comparator PWM block is currently supporting. So directly we can able to, for example, for this example, we are taking this in analog domain or the PWM part, which I'm running in the PSIM. So earlier versions, it is not supporting, but right now it will convert the equivalent 3-phase PWM and we can able to design, we can able to run the same in DSIM also. So that is one feature we have provided. And the same with the discretization also. Here we are providing analog PA controller. So this particular S domain block will be automatically discretized into digital part. So we have S to Z converter in the PSIM part. So the same way internally it will utilize that particular feature. So by using backward Euler method, and it will convert into the discrete domain. So the analog domain will convert into the discrete domain directly. And around 50 new elements we added into this particular 2021b version. So all these blocks we can able to see. Earlier these blocks are not available, but currently we added all these blocks into this new version part. And around 20 plus examples we added, which will be helpful for the academic people or for the research people. So they can able to evaluate, they can able to utilize this as a project part, and they can able to submit their thesis also. So they can able to do further analysis in this particular DSIM. Hope this is clear on the DSIM part. Let me show you on the SmartCtrl features, which is going to release in this month or by first week of March. So as you know, SmartCtrl is for control application for your power electronics. So it has a ready-made templates, or you can able to import the frequency response. So in the latest version, we are in the latest upcoming version. In the upcoming version, we are going to add these topologies, predefined topologies. Already we have a predefined topologies. Compared to that, we are adding the new DC-DC convert topology, that is phase shift dual active bridge with the 2 different control models and 2 possible loads. So the load also you can able to vary. Earlier we have to change only one load. Now we can able to vary multiple loads also. Okay, so and we have improved general improvement in the plant dialogs, that is transfer functions, and even we have provided the direct waveforms with the different waveforms we can able to take it. Earlier we used to get only the magnitude plot, phase plot, and Nyquist plot, and time domain analysis. Apart from that, we should have some waveforms like inductor current values and ripple values. So apart from that, we added different waveforms. And even we are going to add the equation editor, the graphics of the equation editor we are going to change. So even they can able to understand the plant model, how it is creating. And it is possible to implement sampling period in the latest version, like plant for sensor and compensator, even when they're working with the digital domain. And we improved the export functionalities. So earlier we used to export to PSIM, so with only simple functionalities. So now we can able to include all these values, and we can able to export into PSIM also. And even we improve the transient response with the user-defined compensator based equations. So they can able to add these equations, and they can able to check their transfer functions. And the one added, the major advantage will be the direct adjustment of PA compensator using KP and TA. So earlier we used to change only the frequency and the phase margin. Now we can able to change KP and TI also. For example, if someone is using on PA controller, so that is the major advantage we are using. So let's see in the phase shift dual active bridge. So this phase shift dual active bridge are frequently used in different applications such as electric transformation, transportation, or renewable energy and smart grids. So as part of the battery chargers and energy storage system. So basically, if you see for battery charging applications, both voltage and current need to be controlled. So we are adding that particular thing to improve the control designing in the design in these two cases. The dual active bridge control mode and current control. I mean, we have both voltage control mode and current control mode using the ER load. I mean, if the battery load we can able to add, so that is with the voltage source and series resistor, so are included in these this particular latest version. And we added the DC bus connection, so which can be used with the voltage control module with ER load. So that can be added over here. So in addition with that, an alternative DAB control. So here you can able to see that we can able to add the voltage control moding and residual load into the is also included. So as I mentioned, we have added different graphs to show to the user. So and the different switching output capacitance like COSS or ZVS also we have added into this latest version. And we can optimum the control loop with best possible bandwidth for this particular calculations can be added over here, which is be high accuracy. And that even it affects, I mean, it is already included with the transformer magnetizing inductance also. So with all these things, we can able to provide the steady state waveforms to review operating point conditions. So these all information we have provided to the user. And there are some general implements in the plant. So just selecting the topology. In the latest version of 5.0 and defining the parameters. So it is possible to get the transfer function. So here we have this option called to generate the transfer functions and waveforms converter in the open loop. Directly you can able to get it in the open loop. So what exactly will happen? So this information allows the user a better understanding to verify it, whether the given valuable information about the dynamics of the plant in order to select the most suitable compensator. So before selecting the compensator, here you can able to verify and you can able to get the basic understanding. So based upon that, the user can resize the window to have a better view. So information including the body plot using the double simple curves. So here you can able to change the curves also and including all the details. So in the same screen, we added the show graphs to show. So different graphs we added like audio success, audio part and output impedance part and open loop part. And this is all the information we can able to provide it to the user. And here we have provided the graphics included in the equation editor. So now in this version, so to the users, it allows to zoom in. So in this particular application, they can able to zoom in to and resize the transfer function in the equation editor. So here we have an equation editor. We have edited, I mean, we can able to provide with high precision part and recalculating and again and to maximize the resolution. So based upon this, we can able to, I mean, from here you can able to add everything and you can able to zoom the particular information also. So the last one will be direct adjustment of KP and TI. So in the earlier version, we used to change it only this particular frequency and the phase margin. So this particular frequency in the phase margin, we can able to vary. So based upon the points, here we are going to change it. Now we added one more option to edit the KP and TI. So this particular information will be helpful in some applications. So where user want to change only KP or only TI. So this will be very helpful. So all these particular features are going to come in the shorter time. So maybe we are going to release either in the Feb end or by March first week, and you can able to utilize it also. So that's it from my side. Any queries, you can able to post it. So myself and Adrian will be there. So I think we took little time. I hope this particular information will be helpful to you. So as we are launched the latest version on all the thing. So yes, Adrian. So I think we can start with the question and answers, and then we can.
Yeah, we have one question from Dinesh.
Yes. I think 1 second. R by L and KP and K and TN, how these are linked for critically damped systems. Example 1 million ohm, 1 milliohm and 150 microohms, and should be KP and TA for critical damp DC power source step response. Oh. Okay. I mean, as we mentioned, still it is not yet released, so I think we can't make a demonstration. But once it has been released, so we will make a separate arrangement for this, and we can able to see that. I think that makes sense, Adrian.
I think we can. You can send. Can you send us your email address, please? I think it will be better for us to check that, because as Vishwa mentioned, we don't have this version actually to show. So this is only slide to show because the version is not ready yet. So it's hard to answer your question actually right now and show you.
Yes,
So please.
but if you have a earlier experience on the smart control, I think that will be easy. So here we have a plant model. So I think I can try to answer your question. So we have a plant model from the predefined topologies, as we mentioned, and based upon the predefined topologies, we can able to select the sensor. If it is a current or voltage sensor, you can able to select, and the compensator. So if it is whether PI or type 2, type 3 PI analog or PI, everything we have. Accordingly, we are going to select the crossover frequency in the phase margin. So we are going to select 1 point. So based upon that, we'll get a Bode plot and Nyquist plot and time response. So here, in general, we used to tune this particular frequency and phase margin. I mean, if you are wearing this particular point in the red point, so the entire waveforms are going to change. So accordingly, you can able to calculate your stability criteria. So based upon the number of poles and number of zeros, so you can able to calculate your stability criteria. So that so this KP and I mean this particular KP and TI, you can able to export, or you can able to directly take in PSIM, and you can able to run further analysis also. So this is the easiest way which you are following in smart control. So hope this answers your basic thing. But if once the software has been released, we can able to provide you in detailed session to you. Yes, we can able to send you the presentation and the recordings. I think it will be uploaded in our website shortly after this particular thing, maybe by tomorrow. I mean, maybe by next week, so you can able to get it. So, any other further queries? Yes, I think that's it from my end and from Adrian, if I'm not wrong. So if any further questions, you can able to post us, we can help you out. There is no accuracy problems. Both the PSIM and DSIM will be the same. So only the solver and the inside algorithm is only difference, but the accuracy will be the same. We don't have any accuracy problems. We'll get the best results. Switching frequency in general, at what frequency you want to run this particular circuit, and the sampling frequency at what rate you want to see the results. So that is the only difference.
And what Vishwa has mentioned is the crossover frequency in the solution map. It's crossover frequency over the phase margin of your system. So it's not sampling here, it's crossover.
Okay, sorry. Yeah, my bad. Sorry, sampling. Crossover frequency, sorry. So this particular sampling frequency will be helpful in the Nyquist plot. So understand the specific sampling rate, so the frequency given. So based upon the switching frequency, we are going to calculate those sampling frequency also. So number of samples you are going to get in that particular frequency. So those points also we can able to mention. We can able to see that. So it should be 2 times of your frequency. The sampling frequency should be 2 times of your frequency. So it should be 1200. So 1.2 kHz. And mostly there will be aliasing effect. So which should user has to take care. So and it should be above an Nyquist rate also. So these two signals they have to provide. Is it linked to accuracy? Yes. If you, if the number of samples are increasing, generally you'll get more accurate. So that you can able to see the more points and the proper waveform. And if the number of points are, sampling frequency is less, and the sampling points will be also low, right? So accordingly, the graph will be minimum. So you'll not get a proper waveform. At 2f, at 2 times of your frequency, you'll get a good accuracy generally, because you are getting a good bandwidth, right, at that particular instant. And mostly you have to consider your sampling frequency is equal to 1 by t in general. So that also you have to take care. So for example, if you are taking some 50 kilohertz, so in that you'll get some 50,000 samples per second. So you want a 0.1% accuracy or 1% accuracy? What exactly that? 0.1 accuracy. So generally the accuracy will be equal to 1, right? If you are getting more parts, so then you have to go for higher frequency itself. Okay. I think it's time to stop it. If you have any further queries, you can able to send us an email and we can able to check it. Already it's half an hour. I think we are half an hour ahead to the consume time. So I think Adam, can we stop this session?
Yes, so Dinesh, if you have any other question, please feel free to contact us directly.
Yes,
we will
have
answer all your
questions
questions, because I think now those questions are not part of the webinar itself. Okay, it is more maybe support directly. So if you are interested in PSIM, DSIM, or SmartCtrl, you can try them and you can ask your question regarding those links. Okay, so you have our email address. And yeah, so thanks everyone for joining the meeting today. I hope you have enjoyed this meeting in order to know the new features. So feel free to contact us directly. and we will answer your question if it is more technical than the meaning of this webinar today.
Yes, thank you everyone. Have a great day. Stay safe. Thank you.
Thank you everyone. Bye bye. Have a good day and take care. Thank you.